I am still, however, concerned about shear in the web of this chord member. So the way I consider this is that I think about the various components of force. In this case, I want them perpendicular to the chord. So I want the components perpendicular to the chord. And I like to think of those as little point loads applied at various places along the chord. Because the joint is in vertical equilibrium, I know that by the time we've transferred all the way through this particular joint, I know that the net effect is zero, but over the zone of this connection, then I've got some interesting effects in the web. I also need to carry out the same consideration in the vertical member, because again, I've got a shear problem. I'm applying a point load at the level of the stiffener to the vertical member. That force is eventually going to dissipate through to the top flange, but in between the two, I must therefore have a shear force. So as well as the main chord, I'm also concerned about the shear in that vertical member. So in the chord, I've drawn myself a little shear force diagram. So you can follow through the direction of those arrows. And I hope that you would agree with me about the various values that you see on the little shear force diagram at the bottom. So worst case, I think I've got, excuse me, just over 1100 kilonewtons of shear towards the middle of that joint. Can my section accommodate 11,000 kilonewtons of shear? Well, let's have a look. And I know that this is just looking at the chord in splendid isolation, and you might have a different view of that because of course it's got the member welded to the top of it, but let's think about it just in isolation. I could look up or I could calculate the shear resistance, and I find it's 1134. So one might say, well, that's all right because it's bigger than 1101. But I absolutely know in the web of the chord I've also got a longitudinal direct stress, because remember it's working at 75% of its resistance. So actually I'm nervous that I do have a problem of combined stresses in the area of the chord web. 75% of the design stress due to the direct tension, and then a very high shear. And we know that we can't enjoy the benefits of high shear and high tension at the same time. If we're designing a member, we know that one of them will have to be reduced, and we expect to find that we get the same problem here. What then are we going to do about verifying the web, which we consider is subject to a shear stress and a tensile stress? Well, I recommend that we are going to use the von Mises criteria. So this is a way of combining stresses. We've got the design effect stresses as numerators, and we've got the design strength as denominators. I think most people would be familiar with this criteria. We need to check that the combination of all these ratios, some squared and some not, is less than 1. We've got a longitudinal stress, sigma x, in the left-hand term, and we've got a shear stress, tau ED, on the very right-hand term. We need to work out what those values are. Well, the one on the left is very easy because we know that ratio is 0.75. I have said consistently now a number of times, it's working at 75% of its design strength. What we need to know is we need to know the elastic shear stress. I'm emphasizing the word elastic because the von Mises criteria that we see on the screen now is an elastic combination of stresses. So normally we would work out a plastic shear stress, but I'm being very pedantic in this case. I'm going to say no, the von Mises criteria is elastic, and therefore I'm going to work out the elastic shear stress. And you remember that's a parabolic form. It's going to be lower towards the flanges and it's going to be higher at the neutral axis of the chord. Here is things which we've long since forgotten. We learnt them when we were back at college. You probably have a different way of remembering this, but I always remember the elastic shear stress is SAY, or SAY over IT. You will perhaps have a slightly different way of remembering that, but I'm sure you're familiar with the calculation of the elastic stress distribution. So we know what the shear is. We know what the second moment of area is. We know what the area, I suppose, of half a section is. We know what the web thickness is. Y bar, the distance to the neutral axis of half a section. That's the bit that we need to do some calculations of. So I've settled down and I've worked out where the neutral axis is of that T-shaped section. Maybe I could have looked at the T-section profiles in the blue book, and that would have perhaps told me where it was, or very close to where it was at least. But anyway, I've worked it out longhand. I calculate therefore SAY over IT as 242. So remember, that's the maximum elastic stress at the neutral axis. And just out of interest, the plastic stress, had we assumed a plastic distribution of stress, a mere 193. So you can kind of see it does make some significant difference. In this case, I don't know, between 20 and 25%, I suppose, the elastic stress higher than the assumed plastic stress distribution. So I put these numbers in, I crank the handle, and out pops a utilization not entirely unexpected at all of 2.03. If we've got a shear stress which is almost at the design resistance, and we're working the longitudinal stress at 75% of its resistance, we should never be surprised that we're going to fail this criteria. So what are we going to do? Well, we're going to reinforce the web in this case. Now I've chosen to reinforce it with a supplementary web plate. Okay, so that's the red rectangle.